Let's begin. So we're going to continue our discussion of section 6.2 in circular motion, specifically our uniform circular motion. What we'll do today is review uniform circular motion again, and then look at a particular instantiation or instance of circular motion. Still uniform circular motion, but now no longer is it horizontal circular motion, which is what we're most familiar with, maybe like a car going around a roundabout, or the apple that I swung around my head on the string. That was horizontal circular motion. The circle that it was going around was horizontal to the ground. Now we'll be looking at circular motion in which the circle that's made, that the object is traversing, is vertical. That's what VCM is, vertical circular motion. This is like the loop-de-loop on a roller coaster. This is also as if I took that swinging apple and then I swung it above my head. It would be up and then down and then up and down. So it would reach above my head and then continuing on in the circle go down to my feet. So that's what we'll be looking at today, and the forces that are involved there. We'll do two problems together. One analyzing a vertical circular motion circumstance, and then an advanced problem in horizontal uniform circular motion. Before watching this video, you should watch the vertical circular motion video I attached to the announcement on Blackboard, and then take a look at section 6.2 and give yourself a read of 6.2 to continue your understanding of circular motion. All right, our review of uniform circular motion. This will be quick. I have our circle here, right? That circle has some radius r, right? We'll represent that with capital R. We have some object that's traveling around or traversing the circle. At any moment in time, we have the direction of that circle, or direction of that object that's traveling that circle, and it's tangent to the circle, right? So there's our velocity that is tangent to the circle. At that moment of time, at some moment in time later, if the object now is traveling this way in the circle, so counterclockwise, then the direction of our object now is still tangent to that circle or touches at one point. So the velocity vector, though it may be the same length, so it has the same magnitude, that velocity vector has changed, and so there must be some acceleration that this object is undergoing. Because there is a change in the velocity vector, then we have some acceleration. We saw last class that acceleration is directed towards the center. So while the velocity may be tangent, the acceleration is perpendicular to that or pointed towards the center of the circle. It's always pointed towards the center of the circle. There's our centripetal acceleration. If we have some centripetal acceleration, then we also have some force that is generating that acceleration. We have a net centripetal force, right? We can quantify both of these quantities. The centripetal acceleration, the magnitude of the centripetal acceleration, is found to be the square of the speed divided by the radius. The magnitude of the centripetal force is the mass of that object times the acceleration it undergoes, just like we see from Newton's second law. We know that the acceleration it's undergoing for circular motion is quantified by the square of the speed divided by the radius. So we'd say the magnitude of the velocity, which is speed, squared divided by r. mv squared over r is how strong our centripetal force is, or the force that's towards the center. We also found that the speed of this object that's traveling around the circle is equal to the magnitude of the velocity. That is the distance around the circle, or the circumference, divided by the time it takes for it to travel around that circumference, or make one revolution. That would be the circumference, which is 2 pi r. That's the distance divided by time. That period is represented by t. This should be a capital R. All right, that's a pretty good review of our uniform circular motion. By uniform, of course, again, we remember constant speed, so this speed remains the same for uniform circular motion. We looked at some problems in horizontal circular motion. Today we'll look at a problem in vertical circular motion. That problem in vertical circular motion will be the same one that is described in the lecture notes that are posted on Blackboard under 6.2. So what we have is a swing set here. So I'm going to have, here's our bar that controls the swing set, and then the swing set that goes down. Make sure that you can see this. All right, very good. Then we have a bar that goes down like this towards the ground, a bar like this that goes towards the ground. So this is a side view of the swing set. And if you will, I can draw the ground here. Draw the ground. Okay, there's our ground. Okay. And then we have someone that's swinging on the swing set. Say they're all the way over here. Okay, there's someone on the swing set. I'll even put a little chair. Right, there's a chair for them. I can draw the person that's on there maybe. There's a person that's on there and their legs are hanging down. Not the greatest design, but right. This chain here that holds on to the center axis of rotation, right, that we would call this our axis of rotation, if you like, axis of rotation. We would call this length the distance that this person is. This person has some mass. That person that has some mass is some distance from the axis of rotation. We call that our radius, right? And you see that there is this circle that they're traversing as they go down the swing, right? They get to the bottom of the swing, and then they start going back up, right? So we have a circumstance of circular motion. Even more so, we have a circumstance of vertical circular motion. This is a vertical circle, just like our loop-de-loop. Now, what our question is we want to relate this to our experience. How do you feel whenever you get to the bottom of the swing? What you should feel is you feel heavier. At the bottom of the swing, you feel heavier than normal. You feel heavier than normal. In other words, your apparent weight has increased. We want to look at what has happened. Why does it feel like you're heavier than you normally are? To undergo that analysis, we need to apply Newton's second law in our understanding of the centripetal force to this person that's on a swing. When this person's at the top of the swing, that's when they feel the lightest. When they get to the bottom, so we'll draw them when they're at the bottom. They're getting to the bottom of the swing. Right? You still have the person here. Legs hanging off, right? Now they're at the bottom of the swing. They've swung through. It's still of a radius r. We want to look at the free body diagram of this person as they get to the bottom of the swing. We draw a dot representing the person, the forces that are acting on that person. There are two forces acting on this person. One is because the person has some mass m, then we have the force of gravity, the weight. The other force is the force that the chair or the seat exerts on the person. We call that the normal force, the force that is perpendicular to the surface of the chair acting on the person. That force is pointing in the opposite direction as the weight. And it ends up being longer than the weight vector. Why? Well, if the person were here, were just sitting on the swing and not swinging back and forth, it would be the same length. Suddenly, whenever you move into circular motion, that normal force gets longer or has a larger magnitude because the normal force now is not only, while they're swinging, the normal force is not only overcoming weight or supporting your weight, that normal force is also the force that keeps you in this circular motion. Remember what we said about uniform circular motion generally. If we're changing velocity, which this person down at the bottom, they're changing velocity, right? Then there must be some acceleration. In order to induce that acceleration, there has to be a centripetal force. That centripetal force is the sum of these two forces here. Both of these forces act along the axis of rotation, right? Here's our axis of rotation at this moment. At this moment over here, here's our axis of rotation, right? So any forces that are acting along that axis of rotation contribute to centripetal force. All right, so if we did the net force, so we looked at the net force in the y dimension here, right? Looked at forces here. Actually, the dimension we're looking at is not just the y dimension, that's actually the centripetal dimension, right? In other words, the forces that are along the axis of rotation. So when we say some of the forces in y, in this particular circumstance, at the bottom of the ride, of the swing here, we see that the y dimension is the centripetal dimension at this moment in time. The up and down is the same as towards or away from the center of the circle. We have two forces. We have the normal force and the weight that are acting along that centripetal axis. That equals mass times our centripetal acceleration. We turn this into magnitudes because we know the direction of the centripetal force and the centripetal acceleration. It's towards the center. So we'd say that the normal force is contributing to the object staying in the circle, right? It's towards the center, whereas the weight is away from the center. So it's working against the object staying. It's working directly against the object staying, in this case our swinger, our person who is swinging on the swing set. It's working against the centripetal motion. That equals mass times the square root of velocity over r, right? M times our centripetal acceleration, and we know that centripetal acceleration is equal to v squared over r, or the magnitude of velocity squared, or speed over r. So now if we want to find how much heavier you feel at the bottom, that force that tells you how heavy you feel is the normal force. That gives you a sense of how heavy you are feeling. So we need to isolate the normal force in this equation. So we'd say, well, the normal force, in other words, how heavy you feel, your apparent weight, is equal to your normal weight plus the force that's necessary to keep you in the circle. That would be our centripetal force. And so if we know these values, if we know how fast you're swinging at the bottom of the swing, we know the radius, if we know the weight, then we can find how much heavier you feel. And we can put in some values for that. If we look at our lecture notes from 6.2 that are posted to Blackboard, we used Alec in 2A as an example. We said his mass was something around 75 kilograms, that the radius of this swing, reasonably something like 3.5 meters, right? 3.5 meters being something like almost 12 feet, right? Maybe about 12 feet. Makes sense. And then that his velocity at the bottom of the swing would reasonably be 2.5 meters every second. So we could find that ultimately, given those values, given a mass of 75 kilograms, given a velocity or speed at the bottom of the swing equal to about 2.5 meters per second, and then a reasonable radius of 3.5 meters. We find, if we do the math, that we say mg plus m times speed squared divided by our radius of 3.5. We found that Alec's normal force in that circumstance, given these values, that his normal force, his apparent weight, was 870 newtons. We see that that is 130 newtons more or heavier than he normally feels. He normally feels 740 newtons of force due to gravity. This is a good example of anytime you're on a swing, or if you're going on a ride through a loop-de-loop, at the bottom of the loop-de-loop on a roller coaster, you feel heavier for a moment at the bottom because the normal force just got stronger, because that normal force now is now not only supporting your weight, it's also contributing to your centripetal motion or your circular motion. All right, there's our example in vertical circular motion. We very simply still apply our understanding of Newton's second law in free body diagrams, but now to what's happening to the person or the object that's undergoing that vertical circular motion. We'll finish this with a more advanced problem in horizontal circular motion. This is the Starship ride that you may have been on at the State Fair of Texas. I remember as a kid going on this ride, and you're being plastered up against the walls. For reference, this is the last page of the 6.2 section notes that are posted on Blackboard. So you can pull that up and maybe look at that Starship ride. It's the 6th page. So this is a description of the Starship ride and the physics related to that Starship ride at the State Fair of Texas. We have a few pieces of information about this problem. We know that the radius of this room, and I'll draw a little circle first so we can actually see what's going on here. Okay. Try to keep drawing this. All right, close enough. Incidentally, this is something that I made as a kid in Mexico many years ago. Saw it in my room and decided to use it as my device used to make a circle. All right, so we have a circle here. We know the radius of this circle. Okay. Here's where the person is plastered up against the wall. We'll draw that in. That's the person where they're plastered up against the wall. They are 4.2 meters from the center of the circle. Okay. The speed of the wall is 9 meters per second, so we would say at tangential velocity. There's our tangential velocity. We know the length of that tangential velocity vector. The magnitude of it is 9.0 meters per second. That's how fast the walls are spinning, and therefore, because you're up against the wall, that's how fast you are spinning. And we also know your mass. The mass of this person that's plastered up against the wall is 55.0 kilograms. Our question is, what is the nature, direction, and magnitude of the centripetal force? That's a really poor sigma. Of the centripetal force that's keeping you, your 55 kilogram body, plastered up against this wall, or the feeling as if you're plastered up against this wall. If we were to look at your free body diagram at that moment in time, we could draw it as such. We'd say here's your body, right? There's a dot representing your body. There are 3 forces that are acting on your body at this point in time. Because you have some mass, we can always draw the weight, right? So we have force of weight. Okay. Because you are pressed up against this wall, your shirt or your jacket or whatever you're wearing is in contact with a surface. That surface, because 2 surfaces are in contact with each other, there's a frictional force, all right? Which direction is that frictional force? First of all, would we say it's a static or a kinetic frictional force? Well, if you're plastered up against the wall and you're not moving up or down along the wall, and so your feet are up off the ground, then where your body wants to go, its motion desires to be down, pulled down by gravity, so the frictional force must be pointed upwards to oppose gravity. How much upwards? It should be the same length, directly opposing gravity. Frictional force, static frictional force, directly opposes gravity, holds you up against the wall, that friction between your shirt or your jacket and the wall itself. If these 2 surfaces are in contact with each other, we have a way of saying or describing what that force is, and that would be the normal force. That is the force that pushes 2 surfaces up against each other, right? Or the force of one surface onto the other. In this circumstance, if we're looking here, our normal force is this force here, right? Pushing from the wall onto our back, through our body, and towards the center of the circle. So we could draw it like this, right? There's our normal force pointing towards, as long as this point right here, as long as this right here is the center. Say that that's the center of our circle, right? Or the axis of rotation. Here would also be the center of our circle, or the axis of rotation, okay? Of course, at any one time, where our body wants to go is along this velocity vector. In order to stop us from traveling in that straight line, where Newton's first law tells us an object in motion would continue in uniform motion or in a straight line, unless acted upon by a net external force. This normal force is the net external force that pushes us back in towards the center of the circle, towards the center of this starship ride. All right, so these are the forces that are acting on our rider, on you, the rider, the 55.0 kilogram rider. The nature of that centripetal force is the normal force. It is the normal force. That is the force that's contributing to your centripetal motion. The direction is towards the center, of course. Now we just need to find the magnitude. The magnitude of the centripetal force, which we know is the normal force, the magnitude of that normal force, or the centripetal force, which is, we know, the normal force here. We know that any centripetal force can be characterized, the net centripetal force, can be characterized by the mass of the object undergoing centripetal motion or circular motion, times the square of his speed, divided by the radius of the circle he is traversing. We know the mass of our rider, 55 kilograms, we know the velocity, and we know the radius. So we can input these values here of a velocity of 9, we'd say, and a mass of 55. So 55 times 9 squared, which is 55 times 81, divided by a radius of 4.2. And we find that the magnitude of the centripetal force, which in this case our centripetal force is the normal force, must be equal to 1,100 newtons of force. 1,100 newtons of force must be applied to this 55 kilogram rider in order to keep them plastered, or rather, actually, to keep them in this circle, to keep moving on this horizontal circle, right? Because this is parallel to the ground. All right, a more advanced question here, since we have our free body diagram with frictional force and weight, we have an understanding of how what the normal force is accomplishing here, but the normal force is also contributing to keeping our rider suspended above the ground. If you remember when I rode this ride, the walls could move up and down a little bit so that your body could leave the ground. Your feet were no longer on the ground. The force that keeps you from falling back towards the ground, or keeping your body from slipping down the edge of the wall, is that frictional force. So let's look and find what must be the coefficient of static friction. What must be the coefficient of static friction between those two surfaces, that is your back and the shirt on your back, and the wall? What must be that minimum coefficient of static friction that keeps you from slipping back down against the wall? In this circumstance, now that we've analyzed centripetal forces, we're going to find that the coefficient of static friction relates to the frictional force, of course. That force is acting in the y dimension, the up and down. So in order to answer this question of static frictional coefficient, we need to look at the forces that are acting in the y dimension. The forces acting in the y dimension, looking at our free body diagram, are the frictional force, pointing upwards, static frictional force, and the weight. That equals the mass times the acceleration in the y dimension. The frictional force is pointing upwards, it's positive. Let's say F of F. Okay. Frictional force is positive, it's pointing up, looking at our free body diagram. Our weight is pointing down. Mass times acceleration in the y dimension. We are not accelerating the y dimension. Like I said, for this problem, we're just stuck against the wall. We're not accelerating up or accelerating down. So mass times acceleration of 0 is 0. So we find that the frictional force acting between our back and the wall must be equivalent to the weight. We see that as well here in our free body diagram. This vector up is the same length as this vector down. Right, the frictional force and weight, we have a more descriptive way, a more mathematical way of defining both of these quantities. We know that the frictional force is always equal to the static frictional coefficient times the normal force. And we know that the weight is always equal to mass times gravity. The normal force we found just a moment ago to be 1,100 newtons. The static frictional coefficient, that's what we're trying to find. What's the minimum static frictional coefficient? We know the normal force. We know the mass is 55.0 kilograms. We know the gravitational constant is 9.80 newtons per kilogram. So we have all the information we need. We need merely to do a bit of algebra to solve for this static coefficient. Divide both sides by the normal force. And so we find that the static frictional coefficient is equal to the mass of our object, 55.0 kilogram rider, times the gravitational field that object is in this case, we're on planet Earth, so 9.80 newtons per kilogram, divided by the normal force that's pushing on that Starship rider of 1,100 newtons. So we find, if we input our numbers, that our coefficient of static friction must be 0.49. Remember, there's no units associated with this number. It's just a number. It's just a relationship between normal force and frictional force. If this value here were any smaller, so if it was 0.48, then the frictional force would be too weak to support the weight. If this was any larger, the answer would not be that then you would accelerate upwards or that you would be pushed upwards, right? This represents a minimum coefficient of static friction. If it was any smaller, it would be insufficient to support the weight. If it was any bigger, it would be stronger than it needs to be, but stronger than it needs to be is just as good, right? All right, let's review this problem once more. What we did was we started by drawing a picture here to get a sense of this rider here that's represented by this shaded in green. There's a normal force that's pushing from the wall that the person is in contact with up against their back towards the center of the circle. That's what is the centripetal force. That's the force that keeps our rider in the circle. The magnitude of that centripetal force is 1100 newtons. Because we have the back of the rider and the wall in contact with each other, we have a force that's exerted between those two surfaces, and that is the normal force. Because there is a normal force and we have two surfaces, we also have a frictional force. That frictional force is oriented upwards to oppose weight, right? Weight wants to pull our rider down. The frictional force is opposing that pull, opposing that motion. By analyzing forces in the y dimension, we see the frictional force is positive, the weight is in the negative direction. An acceleration of 0 in the y dimension gives us mass times 0 equals 0. We have a more descriptive way of describing or of writing both of these forces. First, the frictional force by the coefficient of static friction times the normal force, and weight by mass times gravity. We're asked to find the minimum static coefficient of friction, so we must isolate that in our equation, divide both sides by the normal force. So we find that we take the mass times gravity divided by the normal force acting on our rider, then we will find that minimum coefficient of static friction. All right, thank you, and please enjoy your Monday of the first week of Advent. I look forward to seeing y'all Wednesday. Bye-bye.